Hi, my name is Mitun Pragji, and I will be presenting my final project on the syringe flange fracture. The purpose of my experiment is to determine if the molded polypropylene syringe will yield under 61.48 newtons at the flange. I will test design variations of the syringe to determine the optimal design to move into production. I currently work at Eli Lilly, which is a pharmaceutical company. I work on the device side, so determining the final strength of certain components of materials is a big concern to make sure devices do not fail in the field. The syringe is a disposable device used to deliver 1 ml of 1 milliliter of drug into a patient or animal. The syringe I will be talking about today is used for an animal since it is a plastic syringe, and currently syringes are mainly glass for holding these strong pharmaceuticals. Syringes can come pre-filled or user-filled. If user-filled, the individual will actually draw the drug out of the vial and then administer it into the patient or animal. There are a few load-bearing surfaces. The nose, which is located basically right under the needle, that'll be loaded after the needle is inserted into the patient or animal. The flange, which is where your index and middle finger go to basically provide a reaction force from loading the plunger rod. And next, as I just mentioned, is the plunger rod, which is loaded by the thumb, which administers the drug. So next I'll be recording the boundary conditions and material properties. As seen on the left, so that is the model of the standard current syringe, just straight transition between the barrel and the flange. The load is 61.48 newtons loaded underneath the flange, so that represents the force of the index and middle finger applied to it during injection. Knowing that, that information is actually got from a human factor study. They studied how much force you could apply with the index finger, and they use like a load cell to do that. More practically, you would actually conduct your own custom procedure, a human factors study actually, to figure out how much those two fingers together will actually apply a force to. As I said, the top is the flange, and the long part is the barrel. And so that's where the drug will be loaded, and the top and bottom of the syringe are fixed supports to figure out where that flange will break. With this, the needle is not included because it does not have a factor in the results. On the right are the material properties. This was gathered from MatWeb. We took them, since it's a range of material properties, has a large range of values that you can get for each one. So I took the average of their range to kind of get the best picture. Although you would actually need to test the actual material once chosen from a certain vendor for the certain grade. The material property that we're most concerned about is the tensile yield strength. This is what we'll be comparing against the results to figure out if we passed or failed. Next, we'll move on to the results now that we have finished the boundary conditions. First thing I evaluated was the equivalent stress, or most commonly known as von Mises. So on the left we have the current model, which is straight. Straight by meaning the barrel to flange transition is straight. No kind of difference there. The middle is the ribbed, and you can see that there is a rib connecting the flange to barrel, which provides more support. And a common practice is to curve an edge to decrease the stress concentrator there. As you can see, the stress is highly concentrated in this area. It is like that for each version, but in the ribbed version, it is shown to be on the rib located right there. With the ribbed, you can see that the stress actually on the flange has decreased. Here, we're looking at the maximum principal stress. So what's the max stress that this can actually withstand? It's kind of the same picture as before. We see that the straight version actually has a higher concentration of stress right at that where the flange meets the barrel, and it's decreased between the when you compare it to the rib and round versions. The total deformation, as expected, because it's more flexible from the outside and it's going to be bending from the center closer to the center, the ends have higher deformation, but not much difference between each version. But I bet if we make the rib longer so it meets the end of the flange, it would definitely make a huge difference there. And the maximum principal plastic strain is the last criteria I was judging on. As we see, it kind of almost follows the same trend as the maximum principal stress, where we see higher strain in the straight version versus the ribbed and round version. So here are the results summed up in a table for each of the versions that I was analyzing. So we have the straight version, the ribbed version, and the rounded version. It was graded upon the criteria I showed before, which are the maximum equivalent stress, maximum principal stress, maximum deformation, and maximum principal plastic strain. The green highlighted numbers show the ones that actually outperform the other two versions. As we see, the ribbed version was the best contender in each category except maximum principal plastic strain. But I find that very insignificant because the plastic strain difference is the difference between 0.0064 and 0.0067, which is very insignificant for this case and practical use. Going back to the purpose of this experiment was to determine if this will actually yield when a person uses it, which is no. According to the bottom right, the tensile yield strength is 186 megapascals, and we have not even come close to that. Which means all versions would be okay, but if we want to optimize it and prepare for the worst, which many designs do, we would choose the ribbed version. So in conclusion, the rib design will decrease the stress and deformation compared to the current model. The pre-filled syringe is actually stored at -5°C. This to preserve the drug. But this will cause the material, since it is a polymer, to perform brittly. And that'll definitely change the results. So physical testing would need to be conducted on prototype parts by the intended molder. So we would typically get tensile bars molded of the grade of plastic we're getting to get the accurate material properties if the vendor does not provide them themselves. And this testing will actually, the model is very accurate for the material properties it uses, but it will need to be tested on actual parts to verify the results. So, and after, like I said before, this product will not yield under human use. Thank you very much.